Okay, let's solve this vitamin C problem another way. This way we'll go directly from the masses that were given instead of going through the percent composition. So, just as a matter of review, empirical formulas tell about ratios of atoms, how many carbons to how many hydrogens to how many oxygens. Moles also tell about the number of particles or atoms and are used to compare ratios. And here's an example, CH4, 1 carbon to 4 hydrogen. That's what that tells us. So just think of atoms as combining in ratios. Okay, and then that is a molecule and that repeats itself. But they have to form in this ratio of 1 carbon to 4 hydrogens. Okay, and then so we are given masses, and moles can be derived from masses if you go through the molar mass conversion. So remember these two conversions. We had the moles to particles or particles to moles, and then moles to molar mass to moles. So for this problem, we're going to go from actual masses to molar masses to moles to empirical formula. So, and then written kind of in a line here, since we are given the masses and we're trying to find, information about the ratio of particles so we can come up with an empirical formula. That is an empirical formula. Then we're going to use conversion unit 2 first, which gets us from actual masses to molar masses and to moles. Gets us from molar masses to moles. We're given the actual masses. And then we'll use the first unit conversion to get from moles to ratio of particles. And that will give us the empirical formula. So let's do it. Okay, here are the given masses for hydrogen, carbon, and oxygen. Using the moles to molar mass unit conversion, we're going to convert this mass into moles. So I'll write the conversions. So I wrote the conversion units, 1 mole of hydrogen over the molar mass of hydrogen. And I wrote molar mass of hydrogen here, but I did not do it for the other ones. But you recognize this as the molar mass of carbon and the molar mass of oxygen from the back of the book. Okay, doing the calculations, I get these numbers. So the grams canceled out. And then I have 10.07 moles for hydrogen, 7.55 for carbon, and 7.55 for oxygen. Okay, so remember from last time, we needed to get the moles into whole numbers because moles indicate whole number ratios. Atoms don't join up in ratios other than whole numbers. So we're going to take the smallest one, 7.550, and divide it into this number, and we will get the number 1. The same thing for this one, and we will not get 1 for this one, but we'll deal with that later. So let me do the math. Okay, so I divided all the numbers by the same number, and I got 2 whole numbers, fantastic, and then 1.33. And notice that there are no units here because we're dividing moles by moles, so we're just getting a number, and this is that coefficient that we're looking for that is going to be in front of each of the atoms to give us the empirical formula. So you should recognize these numbers from the last time we did it, and we'll do the same trick where we'll multiply this number by 2, by 3, by 4 to figure out which number will give us a whole number, and then we'll multiply all 3 numbers by that same whole number. So let me do that. So here's the math for that. When we multiply 1.33 by 2, 3, and 4, we get not a whole number, really close to a whole number, and not a whole number. So we're going to choose this one. So 3 is the magic number to multiply all the other mole ratio numbers by. So we're going to get 4, and that corresponds to hydrogen. 1 times 3, and 1 times 3 corresponding to carbon and oxygen. And these numbers, again, 1.331 and 1 come from up here where we figured out the ratios. All right, so we'll just plug those into the empirical formula. 3 carbons, 4 hydrogens, 3 oxygens. The exact same answer that we got before when we went through the percent composition. So, all right.